Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In the last video we began looking at binary search. We implemented our binary search, at least using an implementation that used a while loop. And before implementing it, we talked about the way in which binary search worked. In this video, I want to show you an alternate implementation of the binary search, and then I also want to show you kind of a look at just how efficient the binary search really is and how it compares to the sequential search. So let's go in and let's edit our file. So we have one binary search here. I want to create another binary search, and we'll call it binary search 2. And this version is going to be recursive. Now, the recursive version actually needs some additional arguments, because what's going to happen is that start and end are going to be recursive elements. So every time it calls itself, it uses a new start and end. We could attach those up here, but then that requires the person who calls the function, who really doesn't need to know about start and end, to provide appropriate values. And I don't want to do that. So instead, what we're going to do is we're actually going to nest another function inside of this function. This is a helper function. It's only needed inside of here. I'll call it the recur helper. It's going to take a start, which is an int, and an end, which is an int, and it's going to return the int for our index. And what does it give you back? Well, first we start with our base cases. So one base case: if start is greater than or equal to end, then we return -1. Else, else, and actually here I will calculate a mid. Val mid equals start plus end over 2. If a sub mid is equal to looking for, then I return mid. Else, well, if a sub mid is greater than looking for, and actually I have to admit I kind of prefer to express the logic the other way. If what I'm looking for is less than a sub mid, then this is where I do my recursive call. Recur helper. Because I'm looking for something that is on the smaller side, the start stays the same, and the end will be mid. Else, so I'm not equal, I'm not less than. That means the thing I'm looking for is greater than, and I call recur helper on mid plus 1 and end. And our main function here simply calls recur helper on 0 and a dot length. And we can try this out. So let's run the version we had before. So 2, 6, 13, and -1. And now if I use the recursive version, 2, 6, 13, -1. Okay, so we get the same answers, the same correct answers, but this version uses a recursive helper function embedded in here. As far as total length, they're about the same. As far as the logic, and actually let's make sure to get rid of our print line in here. As far as how clean the logic is, part of this depends upon, this is an issue of preference. I would argue that the logic on the recursive helper is a little bit simpler than the logic on the while loop. If nothing else, I can say I didn't screw this one up the first time I wrote it, whereas I had in my while loop I had the conditions inverted. So that's a bit of something that you can decide for yourself, but this is an alternate way of writing this. So the next question becomes, how efficient are these functions? Okay, how efficient is binary search compared to the sequential search? So we've already established the sequential search is order n. Okay, if I have n things, on average, assuming the thing I'm looking for, on average, I'm going to have to walk through n over 2. Okay, so I'm going to have to go through half of the elements. On the other hand, a binary search doesn't have to do that. What our binary search does is it starts off and so if I have n values, the first thing it does is it looks in the middle and it does a comparison. It's possible it finds it, but if n is really big, the odds of finding it on the first comparison are very small, and then it cuts down so that we have n over 2 values. I'll use a lowercase. So we have n over 2, and then we have n over 4, and then we have n over 8, and this continues until we get down to 4 elements, and then 2 elements, and then 1 element eventually. Once we get down to 1 element, either we found it or it's not there. Now it turns out that half of the elements in here we won't find until we get down to 1. So this is the maximum number of comparisons that we have to do. And so the question is, well, how many is this? Okay, how many levels are there in this? Well, we can express that by saying, so if we go from the bottom up, so this is the first level, second level, third level, fourth, fifth, sixth, seventh, eighth, up to n. Each of these is a power of 2. So here's 1. This is 2 to the 0, 2 to the 1, 2 to the 2. The next number up will be 2 to the 3, 2 to the 4. So 2 raised to the power of, I'll call it L for level, equals n. And if you remember how to then solve for L, L equals the log base 2 of n. Okay. So the order of our binary searches is logarithmic. Now, how good is that? So if we did a comparison of between these things, one of the little facts that I like to keep inside of my head, and actually if you're going to do things on computers, because binary numbers are significant, but you generally think in decimal, there's a nice little thing to remember, which is that 2 raised to the 10th power is roughly equal to 10 to the 3rd power. And technically, it's equal to 1024, and 1024 is roughly equal to 1000, 10 to the 3rd. So this helps you do quick powers of 2. So if I make a little table here for the sequential, so I have an n value, I have how many things I do on a sequential search, and I have how many comparisons things, let's be specific, how many comparisons I do on my binary search. So if I have 1,000 elements, my sequential will do about 500 comparisons. My binary search will do 10. That's a pretty good improvement, and it's a factor of 50. That's not exactly a small improvement. But wait, it gets better. What if I had 1,000,000 elements? So I'll write this in scientific notation. Well, then I would expect to do 5 times 10 to the 5 on a sequential search, assuming it's there. Of course, if it's not there, that number actually gets larger. For the binary search, though, I do 20. I will do roughly 20 comparisons in order to get to my value. What if I had a really big data set? What if I had 1 billion elements in my data set? Well, then the sequential search is going to do 500 million comparisons in order to find it on average. Our binary search is going to do 30. Okay. And actually, in some ways, this is the average. This is the max. Okay. Now, it turns out that the max in this case is pretty much the average. The average is 29, but yeah, so the binary search isn't just better, it's vastly better. And especially as the data sets get larger and larger, the difference between being order n and running through everything and being order log n becomes larger and larger. When you get to data sets that are truly huge, the sequential search becomes something that you're not willing to wait for. whereas the binary search will happen still very, very quickly. So this is why the binary search is so significant to us. And it's our first example of something in this class where you have a log-based order. We'll see a lot more of this through the later on here and also through the second half of the book, because it's very powerful. The logarithmic growth is nice and slow, and if you can get things that have logarithmic growth, they wind up running very, very fast. So that's it for this video, and we'll come back next time and we'll talk about how we could actually time our performance on these things if